Welcome to algorithms and scheduling. Very specifically, we're talking about rideshare systems. They're also sometimes called on-demand, curb-to-curb, microtransit. There's a lot of other names in there too, and this can easily extend into any kind of setup where you're sharing rides and you're having to pick people up and drop them off. My name is Richard Kirschner, and I put together it took me about 8 weeks to build a beta testing for different algorithms and how they affect scheduling on these systems. It's a huge deal. And from my own experience, the one I was in, I worked in there for about 6 years. I still work there part-time. I found that it was a very inefficient system. There's a lot of things to be desired and a lot of problems that come up from specifically the algorithm side. That's not to say that this is just one small piece of a full business. I'm also looking for work, contract work, or even full-time employment, part-time employment. You can definitely get a hold of me. info@richardkirschner.com will reach me on the email setup. So an overview. This particular video, we're just going to cover the basics. I'm not going to get too much in depth. If you want to look at a full in-depth setup on there, you can go to the GitHub and take a look at that. And I do have documents posted there as far as what I found out and what's going on with that. So we're going to get in a little bit about what do we mean, why this is important. Why do these algorithms make such a big difference? Some of them, I say efficiency. Well, what does that actually mean in dollars and time? We're going to look at the main algorithm, and we're going to define a little bit what's going on in there. I'm not going to get too much in detail to the different algorithms at work. I'll probably address one of them, the one that I've been exposed to that has been around for 20 years. It's about 15 years outdated. It should have been updated a long time ago. And because we're talking about scheduling and algorithms, there's some other major issues that come up when we're doing scheduling. One of them is traffic. How do we deal with traffic hour versus non-traffic hour? Because when you do the scheduling, you don't know what the traffic looks like. You have to guess. We're going to talk a little bit about the speedster driver. This really affects scheduling and why it's a problem, what goes on with that, and also misentries. These are things that also need to be looked at that cause havoc and trouble with scheduling as far as the actual automated part, the programming side. So what do we mean? Well, we have a pickup and a drop-off. That's the basics. And you can see here I grabbed some stuff off of, I guess it's a Front Runner. That's their sales site trying to sell you the little mini bus van, and another one from Sprinter van. These vehicles go from curb to curb. They have a pickup and a drop-off. And somebody might have disabilities. You can see the ramp there. Not included in this is when you're looking at these buses, you really need to make sure they're accessible. That ramp there, real low to the ground, if this bus is going to curb all the time, that ramp's going to have a problem. So those are things to be looked at, but that's not part of the algorithms. That's part of the overall running of the system. And it's about affordable city travel. So why would you have a ride share? Well, if I'm somebody using a ride share, I'm doing it because I can't afford a limousine, or I don't have unlimited money to pay taxi cabs or any of those. There's also the fact that it uses less resources, that we have the ability to bring down the pollution in the air and that kind of stuff. Also bring down the amount of traffic on the road. So when you have one bus out there with taking care of 6 people, we don't have 6 cars out there at the same time. Other people might use it because they have disabilities. They can no longer see. They can no longer drive safely. Or maybe they don't want to drive regularly because they don't feel safe driving anymore. Certainly that's a lot of the passengers that we see on these kinds of systems. We want a safe ride. The last thing you want is someone breezing through town, bumping into people. So it's really about safety. So affordable city travel, pick up and drop off, and a safe ride, and a timely ride. It doesn't do you any good if you're going to a doctor's appointment and it's a 3-hour drive to get there and you miss your doctor's appointment. I understand, that this is a lot of times that it's at a discounted rate. It's sponsored by the public transportation set up in there. But at the same time, we still want people to get to their destination in a timely fashion. They shouldn't have to spend 4 hours getting to their destination By then, imagine the bathroom stops, or even an hour. An hour is a very long ride for a lot of these people who might be on oxygen. They're going to the grocery store. They only have 3 hours. By the time they get to the grocery store, they have just barely a little time to shop, and then they have to schedule way ahead to get home to make sure they're home in time. So what we mean is we're creating a route. That's when we get down to the actual algorithm, is we want to create a route for the vehicle. How does it come in there? The first problem is that this falls underneath what they call traveling salesmen. There's a lot of papers out there on like getting cement mixers and out, because cement mixers have come in and they have to have so much time in mixing, and then they go out, they pour the cement, then they have to go back and get more and that kind of thing. There's a lot of academic papers on these with really extensive mathematics on them. What I didn't find is what happens when it's a one at a time request. They come in one at a time. First passenger calls in, requests a ride, they get it scheduled. Second person has to schedule a ride, and then they have to figure out how do you optimize that ride connected to the first person if they overlap. And there each one is requesting a pickup time, pickup location, and a drop-off location. So it's pretty straightforward. You know, you're getting a ride. I'm going from point A to point B. That is the service. Why is this important? Well, this is very specifically to a ride that came up, and it comes up every Thursday. And it deals with 3 passengers, and they come up regularly. The first passenger is usually going to the grocery store. He's actually got a subscription. For him to get to the bus route on the main street, which is 287, is a 4-block walk. And then he has to walk across the parking lot to the grocery store. And he's an elderly man. I mean, he's not really old, and he could probably get by okay on it. But imagine in a snowstorm, this is his once a week. He gets out and gets groceries, and he gets 2-3 bags of groceries. Then we put a second passenger in there. And the way this current scheduling works, this is an actual route that it generates, is that the second passenger, who happened to find out from the first passenger about the service, schedules a ride at 1 o'clock, same time. But they're going home from Walmart Supercenter, a shopping center, and they go back to where the first passenger is. Now, the way the current algorithm works that's set up is it's based on time, and it says, hey, here's number 1. We're going to schedule them. And then I can fit number 2 is also once at 1 o'clock, and I can also fit their drop-off in, and then we'll drop off passenger number 1. So it goes 1, 2, 2, 1. And you can see here, we literally pick up passenger 1, drive up, pick up passenger 2, drive back down. They've now gone twice past the grocery store to drop them off. Passenger number 2 to drop them off at the place where we picked up passenger number 1 who's still sitting on the bus. And you can imagine if we throw a third person in there who happens to also go out regularly at the same time, and this person happens to be going to Walmart. Sometimes they go to King Soopers, sometimes Walmart. We pick them up. So now we have passenger 1, 2, 3. We drop off 3, 2, 1. And if you can't even see the route on here because they're all overlapping, but poor passenger 1, they go past the grocery store up to the convenience store to pick up passenger 2. We go to there, we pick up passenger 2. We go down to pick up passenger 3, again passing the grocery store. We then take passenger 3 back up to Walmart, where the second passenger was picked up, again passing the grocery store. We then take that person and drop them off at home. And then, after driving past the grocery store 4 times, we then finally take passenger 1 there, and a 6-minute drive turns into a 31-minute drive. If you were watching the times, you would have noticed that they're now been on the bus for a half hour instead of just 6, 7, 8 minutes. As goofy as this is the route. This route comes up regularly, and it's time-based. It's time-based on the scheduling, and that, again, that's the one that I'm exposed to, that I've seen, where we have a pickup 1, pickup 2, pickup 3, drop off 3, drop off 2, drop off 1. And this poor person is now driving around back and forth, up and down. You start expanding that across 3 dimensions, and you get people who are stuck on the bus going around the whole town. Add in a train, some traffic, some orange cones, and suddenly that person who has a limit of 45 minutes on the bus is now on the bus for an hour and 15 minutes. And if the bus is running late or the algorithms are running late, which we'll talk about in other problems that come up, this becomes a very unuseful system for them, and yet this particular individual, passenger number one, that is how they get around. They don't have a car. They can't afford it. So when we talk about why is this important, we have frustrated passengers. It really degrades the service. The user experience, the passenger experience, is not really that much fun for them. When we talk about passengers not having fun, the driver stress goes up. It's a safety issue. Why we now have this person who's like screaming at the driver, "There's my pass off." They're ringing the bell. It could be that they say, "Hey, just let me off over here and I'm going to cross 4 lanes of traffic." That actually happened once on my bus. Somebody decided they did not want to go all the way up and come back and get dropped off, and they wanted to go across 5 lanes of traffic down, the main road there. It just happened to be, it reminded me because it was at that particular intersection, that King Soopers. And it's just not efficient. It costs more. It costs the company more. So there's a price tag attached to it as far as the cost of running this. So when we define main algorithm, this is when we decide when to pick up, decides when to drop off. We have a pick up, drop off slot, and across multiple requests. So we have multiple people calling in. When we look at all this, and we're doing it one at a time, it comes in, and here we go. You can see I had passenger 1 call in, passenger 2 call in, passenger 3 call in. In this case, passenger 1, I added out on the bottom, is going home. I used a different route on here. I wanted to just mix up the addresses, and these are also made-up addresses. The other one actually had real addresses in it. So these are just made-up addresses in here. But you start to see that this is really a challenge. This isn't the standard salesman problem or sending out deliveries, because you don't know ahead of time all the rides. You know them one at a time, and you have to schedule them one at a time. And so what you end up with on this is you ended schedule stops. And you can see here we have a total of 8 stops. Doing computer program, we always go 0 to 7 instead of 1 to 8. It gets really confusing, but you're always spot 0 when you're dealing with an array. And you can just see here that this is what the driver sees. The driver sees a time, they see the passenger, who they're picking up usually, and where they're going. And they just go from stop to stop to stop to stop. And we know the times in between. So this is really what we're talking about when we're defining these algorithms, is how do we create this manifest, this scheduling for the driver to get all of their customers and pick them up and get them to the location, their destination. So when we get into the main algorithm, we'll do a little zoom in on the route. This is just kind of continuation of what we're doing. This is what some of these route looks like. This was just the first one that was printed out based on sorted by time. And you can see here we have a stop at 1. The driver drives all the way up to 2, drives over to stop 3. This is in red. Those are all pickups. And then they go drop off number 3. Then they go down and drop off the second passenger at stop 5. And then they go all the way up to number 6. This was generated by a time sequence. How close can we get to their pickup time? And then we just keep pushing people's drop-offs out to keep fitting stuff in. 1, 2, 3, 3, 2, 1. That's the pattern that's going to form on this. So what we're looking at, a little bit more details for the company, this is really the bottom line: time and money, drive distance. How much distance are we driving? That's the wear and tear on the vehicle. That's the extra cost in maintenance. These are the things that a poor algorithm is going to cost. It costs the company. It costs whoever's running this. It costs the municipalities. So if you're paying for this, for a company to do this, and they're not optimizing their algorithms, it's costing you. It's costing the bottom dollar. For the passengers, we're dealing with the availability and ride times. Denials and time on board the bus. How long are they going to spend driving around town on the bus? Do they spend an hour on the bus, or do they spend 6 minutes or 30 minutes? The availability, how many times they're denied a ride, also feeds into the cost. If you need to put out an extra bus to handle these extra riders because they're being denied services all the time, you lose money. You have to pay for a whole nother bus, a whole nother driver, maintenance on that bus, and everything else. It turns out, though, that with most of these algorithms, they really don't have as big of an effect on the availability as I thought they would. I thought that would be the biggest impact. It really isn't. We'll talk about that just here in a second as we get into further down with what was discovered in the beta test. Now, this is a beta test. I downloaded the data basically from Zillow. I just looked up houses that were for sale. I tried to get different parts of town, threw in some businesses, and ran the tests on there. Not a good way to run the test. It's not live data. So this is very preliminary. And the first thing we found out is that there was a decrease with some of the algorithms up to 25% from the time one. I use the time as a basis because that's actually the worst one out there. It works. There's reasons that they use it as far as computer resources and why it works. But as far as the choices of algorithms, it definitely is the bottom of the heap. And we were able to increase or decrease the resources used so you're only using 75% of the same drive distance in the manifest. This isn't the overall getting the bus to the area, getting it back to the yard and all that. This is just in the actual drive area, which saves money for the company and again for whoever is paying for it. Usually we're talking about public transportation as municipalities in the region. We saw a 6% increase with some of the algorithms in request validation. I was surprised at this. I was expecting this to be huge. I thought for sure we'd be able to fit more rides in if we set them up a certain way and did different algorithms, whether using a vector approach or using a distance approach or time scale, all these different options. Really only came down to about a 6% increase in requests. It turns out when you push people's drop-offs way back, you can fit a lot more people in, and as you zigzag around, you just keep adding them into the weird zigzags. So you really don't increase the validation rate, but you do mess everything else up. Very specifically, the passenger's ride time. In our test of these algorithms in this beta test, we could decrease the time the passengers on the bus by like 70%. 70%, that's huge. This isn't cutting the ride in half. This is cutting it in almost 3/4, just taking it way down there, or a third. We're taking 2/3 of their ride time off. So instead of being on the bus, taking a grand tour of the town, they get to actually go where they're going. This is the service. We go from point A to point B, and we want to get there in a timely fashion. So as far as user experience, that is huge. That's a huge difference. So what's next with our algorithms? I told you it was a beta test that I put together. Again, you can go to GitHub and take a look at that under Richard-Kirschner. The next thing would be to take more data. Again, I only had 68 addresses, and I randomly selected going from one address to the other. The reason I was limited to 68 was because Google licensing, because I use Google Maps to figure out where they're going, would cut me off there. In fact, I got a big warning note, and I had to send them a special note saying this is for trial. I'm not using this for scamming your company and scraping data. And 68 was sort of the limit. I actually kind of got by with a few extra there after I got the alarm. Live data. The data I did use is live, but it would be nice to actually have the actual system in use and have that actual addresses as far as the setup. It would also mean that if we're testing these different algorithms, having a mapping system instead of using Google Maps, which wasn't, when I did it, I used an API to call it and pull the information, but I didn't have a license. It'd have to be a licensed mapping service. Multiple buses is a big thing. How do you handle multiple buses with this kind of algorithm? There's actually a trick to it, which we'll cover in just a second. Different scenarios. Some of the stuff we didn't go into is what happens when you delete rides. Does that mess up the ride? One of the markers would be how long do you sit in front of someone's house? If you remember that other one, you're doing this weird star all over the place. What happens if I have a pickup here, and a pickup way out here, and another pickup down here, and this person drops out? This pickup time, I will show up 10 minutes early with 2 people on the bus. So I'm sitting there with a bunch of people on the bus waiting for another person because somebody canceled out, and it was not a very well routed setup. The algorithm did not route it in a good way that would work. And we were talking about multiple buses. Weights is really the key. we want to find a way to take all the different options where you could schedule this person's for their pickup and drop off and give them a weight. Now, just jumping a little bit into the technical side, if I weighted on the drive time, that means I'm calling a mapping algorithm. And every time I call that mapping algorithm, it uses a lot of resources. If I'm using some kind of vector where I just use the XY components and figure it out, which I did put in there, I don't have to use that mapping service every time. It might be that, and it's very quick to add and subtract vectors in on a computer. So there's a lot of different things on there, but generating weights and actually organizing all the different options and saying, hey, let's start with this one because it's optimal for the lowest time ride on the bus. And then we'll just go down the list until we find one setup that works. This leads us into other issues. I'm always wondering, because I'm focused on algorithms and scheduling, well, part of an algorithm that comes in is the traffic hour. There's also the speedster driver. There's always those drivers who have to go a little too fast. We've had a couple of them. One of my passengers described the driver, he no longer drives, it was always an interesting trip, and I was always there on time. Not exactly what you want to hear for a safe ride for all your passengers. And bad entries. We get bad entries all the time in these databases on the manifest, and so when it's scheduling, it will actually take those bad entries going in and mess up the schedule. So what does that mean? Well, when we talk about a traffic hour, right now it uses averages, the system I'm involved in. And you'll see there's a nice bell curve that I've put up there, and I have marks on there. Don't have to get too much into the marks and what it all means, but this is kind of the distribution of how late we are to rides because of traffic. And you can usually divide it in half. You can also, very commonly done, is divide it into quarters. I'm going to go into that in just a moment. The current one, though, is that we do an average. And so an average means that when I show up for that first pickup, I have one passenger. That means I'm late 50% of the time. And we bumped the time allotted for the ride. So I'm going to be late 50% of the time, and I'm going to be on time 50% of the time. And this might be from traffic hour 4 to 5. So we tack on 2 minutes instead of 1 minute, or doing 0 minutes. You just always be late in traffic time, and it'd just be a disaster. So they said, hey, let's tack on some time. When you get the second drop off, so you have one passenger, so half of those that you're on time on, you're now late on half of those. So it comes out 37.5%. And you might say, well, what happens if you're ahead? You can catch up a little bit on those ones that you're ahead. Coming up from the other one, that's why it's not 25%, it's 37.5%. But you really can't show up early for pickups. So if you show up early for pickups, you don't get to carry that over. The person's still coming out. They're moving slowly. They figure you're ahead of schedule. Sometimes they'll be ready early, but usually you end up not getting that extra time. What we do with 3/4 is we look at that line where we put a quarter of the rides that are now the top quarter, the ones that were way early on, and then we put 3/4 the other way. That means that we're only behind a quarter of the time that first ride. Right off the bat, I'm 75% of the time ahead of schedule, and I'm 25% of the time behind. The way that runs is as I get into 3 passengers, I'm never that far behind. You'll see on the third passenger, which is 6 stops, I'm still only 50% on time and 50% behind time. What happens is the first one is you're setting up drivers to fail. Let's just go back and take a look at that. Give me a second here to go back one. Whoops. There we go. It's a PowerPoint slide put together with, there we go. Okay, so if we look at this, I want you to think about this as a person whose job is to get people, pick them up, deliver them in a timely fashion, that after 3 passengers, 6 stops, you have a chance of success of 15%, less than 15%. That's your chance of success. You're basically setting up drivers to fail. Our natural compulsion is not to fail as human beings. I guess maybe you should teach classes in psychology on how to deal with failure as a driver, if that's what you want to do. So what happens is now people drive a little faster because they don't want to be behind all the time. So you get a busy hour and I'm just streaming down there and I feel like I'm going to be in the zone, and I continue to get faster and faster and faster and faster. When you set up people to fail, you set up a safety issue. And this safety issue is huge. It's huge. When you use a 3/4 rule, you're setting people up for success. And the psychology, there's a second psychology that kicks in there. If I'm showing up early for all my rides because I'm driving fast, guess what happens? I start slowing down. So the 3/4 rule forces drivers to drive safely. It forces them to drive the speed limit. I didn't invent the 3/4 rule. It's a project management term. They use it for delivery, scheduling, project, guessing how long a project is going to take. They use the 3/4 rule. So this is a very common rule. It's been out there for a long time. If the company you have set up doing your microtransit system, your on-demand or whatever, curb-to-curb setup shared system, make sure they're using the 3/4 rule. You might think that it doesn't make a huge difference, but when you have to replace a $80,000 vehicle and your insurance goes up and you have to find another driver because that driver is no longer allowed to drive because they were in an accident, that's a huge expense. You just lost a lot of money. This 3/4 rule is very big, and it's worth a lot of money to put it into your setup. Now, speedster driver, I talked a little bit about that, and I want you to think about this. If you have a speedster driver and they're adjusting the times every hour, and I once had another co-driver come up and they go, "I'm always on time. I'm always there. I always make it on time." I told you about the guy who was always interesting but always on time. All the other drivers are always late. So not only do you have like a 15% chance of success of being on time with 6 passengers, 6 stops, 3 passengers. The drivers who are speeding just destroy that. So that means everybody else fails. Everybody else who's driving and trying to get passengers timely to their doctor's appointments, to work on time, all that stuff, they all fail. So really kicking in with the 3/4 time or adjusting the time limit, if you have to do it manually, to keep pushing that down a little bit, not too much, because you want to maximize the use of the service, is very important. It makes a big difference. You can also do statistics to find out which drivers are speeding, but if you use the 3/4 rule, it'll naturally bring it down. It'll naturally slow that down. Bad entries is another one we see all the time. What is a bad entry? I'm driving along, I'm trying to hit the drop-off button, but I accidentally hit the different button, and instead of doing a drop-off, I destroy the person's route, I hit the undo, and pretty soon all the stuff comes back, and now I'm at the drop-off, or maybe I forgot to board the person, and I hit the board button, and I hit the drop-off. Well, that just came out as a 0, and with the software that I work with, that I'm as a driver looking at, it comes up and it says, "Hey, you can go across town in 1 minute," and it averages that into all the other rides. And so now all my rides in traffic hour, instead of giving me 2 extra minutes or 3 extra minutes, they give me a -1 minute. It actually takes it down, and so now I have to speed, and now it's extremely dangerous. These are called the abnormalities, anomaly detection, outliers. The technology in software for doing that is just so common now that it's really easy to pull them out with code. Besides the obvious one that anything that is zeroed out or underneath half the drive distance should be removed, they now have, like in Python programming, there's the scikit that has the sklearn with local outlier factor, which brings those out, and you can actually just pull them out. Java has some similar tools like k-means, isolation forest, local outlier factory. I know a little technical for this, but the tools are out there. The tools are out there to take out bad entries. So I covered a lot in this, probably more than should be put in this little 15, 16-minute video. But algorithms are important when you're dealing with ride sharing, and having an optimal ride-sharing algorithms for doing your scheduling is really important. There's a lot of other important things. Training for the drivers and public relations and all that, and as far as being in the management side and planning ahead, all those things are important. But if you're not going in and fixing your rideshare algorithms, and you're not improving them, and you're leaving them at 15 years old, you're putting stuff on the table for a higher rate of accidents, you're putting it on for less customer satisfaction, and you're wasting money and resources. Again, my name is Richard Kirschner. You can go to GitHub, Richard-Kirschner, it's on there. All the stuff that I tested, as far as about 6 different algorithms I tested, are on there. And you can also send me a note, info@richardkirschner.com. Anything you send to richardkirschner.com will get to me. Just let me know if you have any questions, or if you're looking for someone to help build an algorithm to do your ride sharing scheduling. Thank you very much. I appreciate your time.